In this lecture, I'm going to give a demonstration of how to use the TI-84 calculator to solve the normal equations and find the least squares estimators for the rocket-propellant data of example 2.1. We'll do this by forming the augmented matrix associated with the normal equations and then performing Gaussian elimination with Jordan reduction on the augmented matrix for the system using the calculator. So let's first review the form of the normal equations for a simple linear regression model. The least squares estimators of the beta parameters, beta 0 and beta 1, in a simple linear regression model are the values of beta 0 hat and beta 1 hat that satisfy the following system of equations. So we have two equations here involving beta 0 hat and beta 1 hat, as well as a number of summary statistics. The equations comprising this system are called the normal equations. Once the data have been observed, the following summary statistics that are involved in the normal equations can be calculated. We have the sample size, the sum of the x's, the uncorrected sum of the squared x's, the sum of the y's, and the uncorrected sum of products of the x's and the y's. The values of these summary statistics are substituted back into the normal equations, becoming coefficients on beta 0 hat and beta 1 hat on the left-hand side of the equation, and constants on the right-hand side. Now, n, the sum of the x's, and the uncorrected sum of the x squared values are the coefficients on beta 0 hat and beta 1 hat, while the sum of the y's and the uncorrected sum of the products of the x's and the y's are the constants. Now the system can then be solved for beta 0 hat and beta 1 hat, and because beta 0 hat and beta 1 hat solve the normal equations, they satisfy the least squares criterion and are therefore the least squares estimators of beta 0 and beta 1. How can the normal equations be solved for beta 0 hat and beta 1 hat? There are a number of approaches, including numerical trial and error, perhaps using visual or graphical aids, algebraic manipulation of the equations in the system, and Gaussian elimination with Jordan reduction of the augmented matrix associated with the normal equations. Now, in this demonstration, we're going to be focusing on Gaussian elimination with Jordan reduction of the augmented matrix for the system, and we're going to do this using the TI-84 calculator. So let's take another look at example 2.1, the rocket-propellant data. And so here's a description of the problem. A rocket motor is manufactured by bonding an igniter propellant and a sustainer propellant together inside of a metal housing. The shear strength of the bond between the two types of propellant is an important quality characteristic. It's suspected that shear strength is related to the age in weeks of the batch of sustainer propellant. An engineer measured the shear strength, which is the response variable y, measured in psi, and age, which is the explanatory variable x, measured in weeks, on 20 different batches of propellant in order to understand and quantify the relationship between shear strength and age. Now the data are shown on the next slide. And so here we have the shear strength and the age of propellant for the 20 samples. And we want to find the least squares estimators for the simple linear regression that's relating shear strength to age by solving the normal equations. Now we've seen in a previous lecture video that the summary statistics are as shown here. All right, and so this is the first step in doing this analysis, is to calculate these summary statistics and then we can plug these into the appropriate locations in the normal equations. Now, we're going to see how to do these calculations on the TI-84 as part of that analysis. So once they've been calculated, we can plug them into the normal equations, and this is what we get. And so we see that those summary statistics, once they've been calculated, become coefficients on beta 0 hat and beta 1 hat on the left-hand side of the equation, as well as the two constants on the right-hand side. And we're also going to see how to construct the augmented matrix for this system on the TI-84 calculator. Now, the augmented system or the augmented matrix for this system is as follows. So we have this 2 by 3 matrix, and the entries in the two rows in the first two columns correspond to the coefficients on beta 0 hat and beta 1 hat, and the values in column 3 correspond to the constants on the right-hand side of those two equations. All right, so what we're going to do next is hop into a demo where we solve the normal equations via Gaussian elimination with Jordan reduction on the TI-84 calculator. So let's take a look. All right, so let's see how we can solve the normal equations on the TI-84 calculator. The first thing we need to do is to enter the data into the calculator, which I've already done. But I do want to show you where it is. And so in the TI-83 and 84 calculators, the data are stored in lists. And those lists can be accessed from the Stat menu. So if we press the Stat button, all right, that brings up our Statistics menu. And the first option is an option to edit a data list. And so if we select that, then that takes us into a screen where we have access to the various lists in the calculator. And you can see that in list 1, I've already entered the values for the explanatory variable x, which is the age of the propellant samples. And then in list 2, I've entered the values for the response variable y, which is the shear strength of the samples. And so now I can exit out of that and get back to my main screen. By the way, notice that at the bottom of the screen here in the middle, I have a key press history. And so if you have a TI-84 and you'd like to follow along and try to replicate what I'm doing, you could make sure that the data are entered into the appropriate list on your calculator, and then you could use these keystrokes to very easily follow along. Okay, so the first thing that we often do when performing a regression analysis is to create a scatter plot of the data to evaluate whether or not there is a relationship between the variables, and if so, what kind of relationship. And we can do that very easily by utilizing the stat plot functionality, which is up here in the top left corner of the calculator. And because that's in blue above the y equal to key, the way we access that stat plot functionality is to press the second key, the blue key, and then the y equal key. And so that brings us to the stat plot menu. And you can see that we have several stat plots available. We're going to be using stat plot 1. And you can see that stat plot 1 is currently on. Stat plots 2, 3, and 4 are off. If we select stat plot 1 and press enter, then that brings us to a wizard that allows us to set up the first stat plot. Right, we could toggle it off or toggle it back on. The type of plot we want is a scatter plot. And that is specified by the first icon here in this row of plot types. And so we'll leave it there. We also need to make sure that we've specified the list correctly for the x variable and the y variable. And so the x list contains the values that are going to be plotted along the horizontal axis, and the y list contains the values that are going to be plotted along the vertical axis. And so we have our x values in list 1, our y values in list 2, and so we've got that specified correctly. We don't need to change anything else, and so we can just quit out of this screen. So we press the second button and then quit. Now, in order to plot the data and be able to see all the data points, we need to make sure that the window is specified correctly. It's big enough and not too big. We want it to be just right. And we could do that by visually inspecting the data ourselves and then going to the window screen by pressing the window button. And we could make sure that the minimum and maximum for both the x-axis and the y-axis are such that all the data points will be displayed. But we really don't have to do that because there's some nice functionality built into this calculator that will do that sizing of the screen for us automatically. And so if I clear out of here, or actually I just want to quit, second quit. If I go up here to zoom, all right, so that would be zooming in the screen on a plot, zooming in, zooming out, and so forth. And you can see here that there are several options. The one we want is option number 9, the zoom stat. And this is going to zoom, it's going to create a stat plot, and it's going to zoom the screen so that the minimum and maximum values on both the x and y axes are such that all of the data points will be visible. Okay, and so it's going to do that automatically. And so if we select option 9, then it goes through and it looks at the data, and again it specifies the minimum and maximum values for x and y axis such that all the data points are displayed. And so we see here that scatter plot of the data containing all 20 data points. From this we can see that there's a decreasing trend between the response variable y, which is shear strength, and the explanatory variable x, which is age. And so the interpretation is that as x increases, as the samples get older, the shear strength decreases. And not only that, but we can see that over the range of ages that we have data for, this relationship can be well approximated by a linear function, right? And so simple linear regression of y versus x makes sense in this situation. Okay, so let's clear out the screen, but before we do, let me go over here to the right-hand side, and what I can do is I can specify in this panel to display the graph. Okay, and then if I redo that, there we go. Okay, then it'll display that, keep that graphic display up there for the duration of what we're doing here. And so now let me clear this out and get back to the main calculator screen. And I think what I'll do, because we're going to move on to something else now, we're going to calculate the summary statistics required to do the analysis. I'm going to clear out the key press history, right? And we'll start with a fresh panel there. So the next thing we need to do is to calculate summary statistics for both of our variables. And the way we do that is to, again, go back into our statistics menu. And now we're going to select the calc menu option. And so we can use a right arrow to move over one option. And then the option we want is to calculate two variable statistics. And so we'll use the down arrow and highlight that option, and then press the Enter key. By the way, whenever you have a menu like this, you can also press the number corresponding to the option, and it will automatically plug in the number and press enter for you. And so we could just press 2 here, and it would take us to this wizard that is prompting us for the two lists containing the data for which we want summary statistics. And so the X variable, again, is stored in list 1, and so this is specified correctly. The Y variable is stored in list 2, and so that is specified correctly. And so now all we have to do is to scroll down and highlight calculate and then press enter. And it calculates the various summary statistics. And on top of that, it's storing these various summary statistics in the statistical registers in the calculator. Now let's just take a look at the various summary statistics that we have available. You can see here that we've got the mean of the X values, the sum of the X values, the uncorrected sum of squares of the X values, and then we have a sample standard deviation and then a sigma. So if the data in the list is considered to be a sample, this is the S would be the standard deviation that we would use. On the other hand, if the data in list 1 were considered to be a population, then sigma would be the standard deviation that we would select. All right, we have the sample size here, and then if I scroll down, I have the same type of summary statistics for the values in list 2. All right, and then notice we also have the uncorrected sum of products of the X's and the Y's. Okay, so by performing or asking for the two sample statistics, two variable statistics, the calculator has done all that calculation for us, and it's populated those the appropriate registers in the statistical memory of the calculator. Now let me just show you what I'm talking about. If we press the vars key, the variables key, you can see that we have several types of variables available in the calculator. And the one we're interested in is option number 5, the variables corresponding to statistics. And you can see here that we have the sample size, the mean of the values in list 1, the standard deviation, the mean of the values in list 2, and so forth. If we scroll over one item, we have summation. So we have the sum of the X values, the sum of the values in list 1, the uncorrected sum of squares of the X values, the sum of the Y values, the uncorrected sum of squares of the Y values, and the uncorrected sum of products. So all of those values can be accessed by just selecting the item we want. So for example, if we wanted the sum of the X's, we could just select that, press enter, and then press enter again. To get the uncorrected sum of squares of the X's, all right, we could go back into vars, select statistics, move over 1 to the summation, and select item number 2. And that gives us the uncorrected sum of squares of the X's. Okay, so that is where we could access those summary statistics when we need them. Now let me just say this, that when you calculate the two variables, or any time you're calculating statistics like we've done, all right, what we don't want to do is to calculate them and then write them down on a piece of paper, and then when we need them for subsequent calculations, we re-enter these values. Because when we do that, there's always the chance that we'll re-enter them wrong. And even if we enter them correctly, we're probably not going to have the same level of precision that the variables have when they're stored in the registers in the calculator. So the calculator has done all these calculations, and it's storing these values in memory locations in the calculator. And more than likely, it's storing the values with greater precision that's even being displayed on the screen. All right, and so if we were to write things down and then enter them back in by hand using the keypad when we needed them, we would more than likely be using values that have less precision than what's already stored in the calculator. So we never want to do that whenever possible. Right? What we want to do is to tell the calculator to calculate the summary statistics, and then if we need to do subsequent calculations with those values, we obtain them by going into the variables menu and then selecting them from the appropriate options here. In fact, ideally, the only thing you should ever be entering into the calculator is the raw data itself in the lists. And once you have the data in the lists, then you do all the calculations in memory. You store those intermediate calculations in the statistical registers of the calculator, and you go and grab them when you need them for subsequent calculations. Okay, so the next thing we're going to do, now that we have calculated the summary statistics, and in particular, we have the summary statistics needed to create the augmented matrix corresponding to the normal equations. And so what we're going to do next is to construct that augmented matrix. Now let me go ahead and clear out the key press history. And by the way, I think what I'll do, I'm going to bring up the graph here, and I'll bring up the data set there. Okay, because we're going to want to look at that data set a little later. Okay, so what we're going to do next is create a matrix in which we can put the values for the augmented matrix for the system. Now, the matrix menu is found in this option. You can see here the matrix in blue over that key. And so to access that, we need to press the blue second key first and then press that key. And so you can see here that we have various matrix variables available to us. And in fact, we have 10 different matrix variables that we can utilize. And so if we need to access the name of the matrix variable, we access it from this menu option. But before we can do anything with it, in fact, let me show you what happens if we try to access a matrix variable before we've actually defined a matrix. And so I selected the A matrix, and if I press enter, it tells me that there's an error that the variable has not been defined yet. And so let's go ahead and quit out of that. And so what we need to do is first create a matrix and assign it to a matrix variable. And so again, we'll go into the matrix menu. And what we need to do is to move over to the edit menu option. And we're going to create a matrix, and let's assign it to matrix variable A. Okay, now we're going to create the augmented matrix for a simple linear regression. And so that's going to be a matrix with 2 rows and 3 columns. And so we'll enter 2 for the number of rows, and then 3 for the number of columns. And then it gives us a 2 by 3 matrix containing all zeros. Now, we need to enter the values from corresponding to the normal equations into this augmented matrix. But again, we're not going to enter them by hand. We're going to go out to the statistical registers and get the values we need. And so if you recall, think of that first equation in the normal equations. Right? So that first row of the matrix corresponds to that first equation. And in this entry, we need to have n. So in that first equation, we have n times beta 0 hat plus, and then the sum of the x's times beta 1 hat, and that's equal to the sum of the y's. And so the value that goes in this cell, the cell in row 1, column 1, is the sum, or is the number of observations. All right, it's n. And so we go to our vars menu, we go down to statistics, all right, and we select the option for the sample size. We can see that displayed there, and if we press enter, it puts in the value. Okay, the entry in row 1, column 2 contains the sum of the x's. And so we get that from our vars menu. Go down to option 5 for statistics. Move over one item there to the summation menu, and then we select option 1 for the sum of the x's. Okay, so that's 267.25. Okay, the next entry is the sum of the y values. And so we go to vars, statistics, sum, and then option 3 for the sum of the y's. Now notice that it displays 42,627, but if we hover over that or move our cursor into that cell, we see that the actual value that's stored there is 42,627.15. So it's rounding. It's only displaying it to 5 digits in each of these, right? But it does have all these values stored with maximum precision. Okay, the entry in the second row, first column, is the sum of the x's. All right, and so we'll go down and go to our var menu, and then statistics, and then the sum of the x's. All right, so again, 267.25. The entry in the second row, second column, is the sum of the squared x's, the uncorrected sum of squares for the x's. And so we go to our vars menu, statistics, sum, and then option 2, the sum of the squared x's. And so that displays 4677.7, all right, but it's actually 4677.6875. And then finally, the entry in row 2, column 3, is the sum of the x's times the y's, the uncorrected sum of products of the x's and the y's. All right, and so we go to our vars key, and then statistics, sum, and then option 5. Okay, so that is 528,492.6375. Okay, so we've entered the entries, the values, into this 2x3 matrix. This is the augmented matrix corresponding to the normal equations. To exit out of here, we're going to press second and then quit. We could view the matrix by pressing second and then matrix, and then selecting the variable A name from the names menu. All right, and so now instead of an error message, it actually displays the matrix. And notice that it's got this right arrow over here. And so what that means is that we could press the right arrow and scroll over and see all the rest of the values, and we could scroll back. Okay, so we've created a 2x3 matrix and entered the appropriate values into that, corresponding to the augmented matrix for the normal equations. And so now what we want to do is we want to perform Gaussian elimination with Jordan reduction on that augmented matrix to get it into what's called reduced row echelon form. And so to do that, I think what I'll do is clear out my key press history again. All right, start fresh down there. And the way we access the functionality to convert it to reduced row echelon form is to go into the matrix menu and then select the math option. Okay, so let me go ahead and do that. And then we want to toggle over or arrow over to the math menu. And then if we arrow down, okay, we'll see that we have a function called RREF. And so what this does is it takes a matrix variable name as an argument, and it performs Gaussian elimination with Jordan reduction on that matrix to convert it to reduced row echelon form. And so let's select that. And then we want to specify matrix A. And so I can go back into my matrix menu and select matrix A, and then close it off with the right parenthesis, and then press enter. And so now we have the transformed version of the augmented matrix, and this is now in reduced row echelon form. Now, before I forget, what I want to do is I'm going to use this matrix in a few moments. What I want to do is save this to another matrix variable. And so let's save it to matrix variable B. And the way that we can do that is to press the store key immediately after doing this calculation. This matrix is stored into what's called the answer variable. And so we're going to store that matrix, which is currently located in the answer variable. We're going to store this in matrix B. Okay, and so there we have it. And we could verify this. Let me select the matrix menu again and tell it to display matrix B, and you can see here that we did successfully store that matrix in matrix B. Okay, so this matrix, let me clear that off. I'm going to display both A and B. Okay, so these two matrices are equivalent in the sense that they correspond to systems of equations that are equivalent. That is, that they have the same solution. Now, the solution for the system corresponding to this augmented matrix is very easy to obtain visually because of this form. The 1 here is the coefficient on beta 0 hat. The 0 is the coefficient on beta 1 hat. And so the equation corresponding to the first row in this matrix is beta 0 hat equal to 2627.822359. All right, and so that tells us the value of beta 0 hat. In the second row, this 0 is the coefficient on beta 0 hat. The 1 is the coefficient on beta 1 hat. And so this tells us that beta 1 hat is equal to negative 37.15359094. So we're able to very easily solve the system of equations by performing Gaussian elimination and Jordan reduction on the augmented matrix for the normal equations, and we can do that on the TI-84 calculator, as we've seen. Okay, so I want to do a few other things. Let's suppose that in addition to finding the least squares estimators of beta 0 hat and beta 1 hat, we also wanted to plot the line. And suppose we also want to calculate the sum of squares error for that line. So let's do the second of those first. Let's calculate the sum of squared errors for this line. And to do that, what I want to do is show you how we can calculate the predicted values of y now that we have the least square solutions here. And so to do that, recall that the predicted value of y, which is y hat, is equal to beta 0 hat plus the product of beta 1 hat and x. Now beta 0 hat is in the first row, third column of the matrix that we're calling B here, and beta 1 hat is in the second row, third column of that matrix. And so it would be nice if we could pull out those values, those entries from that B matrix. And we can actually do that. It's very easy to do. So the way we do that is to first grab the B matrix variable, and we could do that by going up and selecting second and then matrix and then selecting the B matrix. But since we already have it displayed here, I wanted to show you what we can do. If I use the arrow key and highlight a value or a variable and then press enter, it's going to copy that and bring it down to the current position on the screen. Okay, now what we need to do is specify the location in the matrix whose value we want to pull out. And we do that by typing in a left parenthesis and then specifying the row and the column of the value we want. Well, 2627 is in the first row and third column. We separate the row and the column by a comma. All right, then close it off with a right parenthesis, and then we press enter, and so now we have beta 0 hat as a scalar. We can do a similar thing to get beta 1 hat. Again, I'm going to take advantage of the fact that I can just copy and paste down here in the current line, and I can use the left arrow key to move over and just change the 1 from row 1 to row 2, and now we have beta 1 hat out here as a scalar that we can use as well. Okay, now to calculate the predicted values of y, all right, recall that the predicted values are given by beta 0 hat plus beta 1 hat times x. Now, the x values are contained in list 1. And so that's what we're going to enter right here. And the way we do that is to press the second key, and then you'll notice that the various lists are located down here. So after we press the second button to gain access to the blue functionality, all right, we press that button. And so now, if we press enter, it's going to apply this function to every x value in list 1. And what it returns is a list. All right, you can see here the left bracket. You can see the right arrow here, so we could scroll over and we can see these different values. Let's go ahead and let's save this list, list of values in, let's see, list 3. All right, so we'll press the store key, and then we'll press second, and then list 3. And so now it has stored that list of predicted values into list 3. Now, if we press the refresh button here, we then see the predicted values. Now, how do we calculate the sum of squares error? Recall that the sum of squares error is the sum of the squares of the differences between the observed y values, which is in list 2, and the predicted y values, which is in list 3. All right, so let me clear off the screen here. And I'm going to go ahead and clear out the key press history. Okay, so let's first calculate the differences between the observed values and the predicted values. All right, and so that would be list 2 minus list 3. And if we press enter, it's going to create a new list containing the differences between corresponding entries in list 2 and list 3. Now, that's not quite what we want. What we want are the squares of those values. And so I will press the left parenthesis key. I'll go up and grab the difference, list 2 minus list 3. Press the right parenthesis key, and then press the squared key and press enter. And so now we have the squared values, the squared differences. Now, let's store that to list 4. Let me refresh. All right, so now list 4 contains the squared differences between corresponding entries in list 2 and list 3. Now finally, the sum of squares error is the sum of the values in list 4. Now we can obtain, or we can access the list functionality to calculate that, and the list functionality is located here. All right, you see list up above this in blue above the stat key, and so we press second and then list. And we want to do some math on a list. In particular, we want to calculate the sum of the values in list 4. Okay, and so this is the sum of the squares of the differences between the observed values and predicted values. And that sum is 166 to 54.8581. And so that is the sum of squares error for this simple linear, or estimated simple linear regression line. Okay, finally, suppose that we want to superimpose a scatter, or I'm sorry, the least squares line over the scatter plot of the data. We can do that by going up here to the y equal to key, where we can specify a function to plot when we graph. And recall that y hat is equal to beta 0 hat plus the product of beta 1 hat and x. Now we know that beta 0 hat is in the entry in matrix B in the first row and the third column. Okay, so that's beta 0 hat plus, and then we go back to matrix B and we select the entry in row 2, column 3. Okay, that is beta 1 hat. And then we multiply that by the variable x, which is obtained by pressing this key. Now, because the window was already sized when we initially did the scatter plot, we don't have to resize it or anything. All we have to do is to press the graph key. And so you can see that in addition to the scatter plot of the original data, we have the least squares line superimposed over the data. And so we get a visual assessment of how well the line fits the data. Okay, so that's what I wanted to show you in this little demo, how we can use the TI-84 to solve the normal equations using Gaussian elimination with Jordan reduction. Now, one of the things I want to tell you is that the TI-84 calculator has a lot of statistical functionality, and in particular, it has the ability to do simple linear regression. So if all we needed to do was a simple linear regression, we could just use the built-in functionality of this calculator. But this calculator does not have the built-in functionality to do a multiple regression model. But we can do multiple regression on this calculator by using the approach that we used in this demo. In particular, we could construct an augmented matrix corresponding to the normal equations for that multiple regression model, and then we could solve the problem, find the least squares estimators of the various beta parameters by invoking the reduced row echelon form function in this calculator. So this will be applicable even after we get out of simple linear regression into multiple regression. So we have used the TI-84 to perform Gaussian elimination with Jordan reduction on the augmented matrix corresponding to the normal equations, converting it to what is called reduced row echelon form. That reduced row echelon form is the rightmost 2x3 matrix on this slide. And that matrix is the augmented matrix for the system of equations shown at the bottom of this slide, which is equivalent to the original system of equations, that being the normal equations, and therefore it has the same solution set. And the big advantage of this system of equations is because we can read the solution directly from the augmented matrix. All right, in particular, beta 0 hat is equal to 2627.82236, and beta 1 hat is negative 37.15359104. So we have solved the normal equations on the TI-84 calculator. All right, and so we see that these values for beta 0 hat, beta 1 hat, because they solve the normal equations, are the least squares estimators of beta 0 and beta 1. And so the least squares estimate of the simple linear regression line is therefore y hat equal to beta 0 hat plus beta 1 hat times x, which is 2627.82236 minus 37.15359.104 times x. So that is just a demonstration of how we can perform simple linear regression by solving the normal equations on the TI-84 calculator. And as I said previously, this can be generalized to linear regression models that have more than one explanatory variable. So it can be generalized to multiple regression, and therefore we can actually do multiple regression on the TI-84 calculator.